morning, ladies and gentlemen. We're from Hong Kong Chinese Women's Club College. The project that we're working on is a study on infectious disease by mathematical modeling. Some pandemics were deadly and devastating, like Black Death and SARS. The spreading of diseases aroused our concern, and we have myriad of questions in our mind. What are the factors influencing the outbreak of diseases? Are there any measures that are essential to prevent the widespread of disease? And what is the most effective and feasible way to deal with the outbreak of disease? The objective of our project is to study how a disease spreads. Throughout the project, we look into disease-related issues. We investigate the effects of a disease by mathematical modeling. In the meantime, we find out the factors influencing the spread of diseases and possible ways to prevent epidemics. Additionally, we try to simulate the situation in Hong Kong. We start with the simplest case, the SI model. We find that the results obtained do not comply with the data of our daily lives. This promises to modify the model, SIS and SIR models. But our daily life situation can be very complicated with lots of variables, so more models are introduced. In each section, we will first give a definition of all the variables and explanation with a diagram. Then differential equations derived from the model are shown. After that, the analysis, graphs, and a conclusion. There are some assumptions in our project. We assume that all people are well mixed, that is, having an equal probability of meeting every person in the population. Also, all variables are continuous and the population size is fixed. Now I'm going to introduce a simple model of an infectious disease, SIS model. Here we categorize people as susceptible people S and infective people R. We define the error as the flow of population from one side to another. The definitions of beta delta T and mu delta T are shown on the PowerPoint. Over a time interval delta T, the change of S is approximately negative beta SI delta T plus mu R delta T. Taking delta T tends to 0, we have the differential equation shown on the PowerPoint. Similarly, we can obtain another differential equation. After solving the above two differential equations, we have these two solutions. Then we can use the two solutions to generate a graph with different values of beta and mu. However, there are some limitations in the SIS model, as people who have antibodies or dead are not considered. So we modified the SIS model into SISR model. There is a new group of people, removed people R, who are either dead or discharged. Now we developed the SIS model into SISR model. A new group R is introduced and the definition of gamma delta T is shown. We'll have three differential equations. Since there are three different variables in the differential equations, it's not easy to solve them. We use numerical simulation to estimate the number of people in different groups and generate a graph with the help of Excel. From the differential equations, delta S approximately equals bracket negative beta Si plus mu I close bracket times delta T. We approximate the value of S at time t by the following sequence, in which we take delta T as 1 day. In the Excel, the first row shows the initial values of S, I, and R. From the second row onwards, we use formula to generate the sequence which represents the values of S, I, and R over time. We can change the values of beta, gamma, and mu. And now we generate the graph by Excel with different values of beta, gamma, and mu. After substituting different values of beta, gamma, and mu, we can generate a graph of fraction of population that gets sick. From the graph, we can see that if beta n over gamma decreases or mu increases, the fraction of population that gets sick will decrease. So in order to prevent the occurrence of epidemic, the values of gamma and mu should increase and the value of beta should decrease. We can take action, for instance, providing vaccination and improving ventilation can decrease the value of beta. and government can provide medicine to patients as soon as possible to increase the value of gamma. There are still some limitations in this model since people who are in incubation period are not considered. As a result, we modified the SISR model into SEIR model, and a new group of people E who are in incubation period, that is, not infectious in this period, is introduced. Here is the case of swine influenza from April 2009 to April 2010. We generate a graph by using the above data. Now we develop the model into SEIR model. One more group of people, exposed people E, is introduced. The definition of alpha delta T is shown. And then we have 4 differential equations. We use numerical simulation again to generate the graph. From the graph, the number of infectious people is much greater than the actual number. As time passes, the number of research on the virus increases, resulting in more effective vaccination or resulting in an increase in antibodies in the citizens. So gamma may vary with time. We think that the recovery rate is related to time, so we assume the recovery rate of infectious people gamma increases with time and with a decreasing slope such that gamma part T is larger than 0 and gamma double part T is smaller than 0. Then we assume gamma T equals C times T to the power K, with C larger than 0 and K lies between 0 and 1. We generate a graph with numerical simulation again. Compare the curve by numerical simulation with the real case. They are similar. So our assumption can fit the real case. Since we can generate a similar graph as the real case, we can estimate the number of people that will be affected, the time that there is the largest number of infectious people, and the time that the epidemic will take. And these are useful to predict how serious the disease is. This leads to another question, how to estimate the values of beta, alpha, C, and K. We can estimate by using the time of the occurrence of the second case of infection, the total number of people who are infected in the first 2 weeks, the time for an infectious person to be removed, and the total number of removed people in the first 2 weeks. After the submission of our project, we continue to study our models, and we fit our models into the case of SARS. And these are the data we use for estimation. The estimated values of beta, alpha, C, and K are shown, and they are used to predict the case of SARS afterwards. Here's the graph we generate. Compared with the real case, there are some errors as the figures are affected by the sample size, the swift response of the government, and delay in reporting cases. Theoretically, the epidemic occurs if DEDT plus DRDT is larger than 0. Then we can have the period of the epidemic T0 equals beta n over C whole to the power 1 over K, and T0 increases with beta 1 over C and 1 over K. In order to shorten the time of the disease being spread out, C and K should be larger. This means the epidemic will no longer occur if there is any medicine which can control the disease as soon as possible. And here is the flowchart of our model and our project. In this project, we developed a model which is applicable in real-life situation. In the further study of SEIR model, we compared our model with the real case of swine influenza and SARS. We succeeded in generating a graph which could better approximate the real case and find out time is an important factor. No matter what, we all learned from this project, and all of us believe that the project is a progress in disease tackling. And yet, this is just a start. There's still a lot more for us to investigate. And this is the end of our presentation. Thank you for your attention.